Saxon Advanced Mathematics, Lesson 22. Ready for a straightforward topic? Absolute value. When you first learned absolute value, you learned that it's a magical positive number maker. No matter what you put inside of absolute value signs, it always comes out as the positive version of that answer. And in the beginning, I asked you to just trust me that that was real, and we didn't really talk about why that is, so now I want to just fill you in a little bit more. If this is a number line, and these are the basic values around there, when we're measuring absolute value, what we're actually measuring is the distance from the number to 0. So this is what we mean when we say the absolute value of 3 is 3. What we're saying is that from 0 to positive 3, it's 3 units. What we're saying over here is that the value from negative 3 to 0 is also 3 units. Okay, so that's the kind of theoretical underpinning to this idea. Yes, this is still true. Absolute value is just always the positive version of that number. But here's why. It's because what we're measuring is the distance from that number to 0, and that's always positive. Okay, now what we do in calculations with absolute value often involves graphing. So we're going to review some of that. We did this all at the end of last year. It might be sort of lost in a blurry haze of end of the year. I'm over it. But we're going to practice graphing this on the number line is where we're going to start. The absolute value of x minus 2 less than 0. Okay? We know that this will just be a number line because there's only one letter. If there's an x and a y, then that tells us, oh, better go to the Cartesian coordinate system. But because we just have one letter, we know this is going to be on a number line, just a basic number line like that. But before we start graphing it, we want to clean this up so it's easier to graph. The first step, we want to isolate the absolute value. So whatever's in between those two absolute value lines, we want that on one side and everything else on the other side. So we better add 2 to both sides, and we'll get that the absolute value of x is less than 2. Okay, now the next step is to split this. What we want to do is get rid of this absolute value sign, and we want to split this into two, what I say, regular inequalities, meaning they won't have absolute values in them. So the first one is always the easy one. We just flick off the absolute value signs. X is less than 2. For the other one, we take the x, we reverse the way that's pointing, and we multiply that by a negative 1. Okay? So then this is what we want to graph. So we're looking for values of x that are less than 2. So I'm going to circle it, not color it in, because that would be if it was also equal to. Circle means it's open. And then negative 2. And we're looking for the values that make both of these come true. So we want only this in-between part. Okay? And that's our final answer. Okay. Do another one. This one, you'll notice, is in the basic notation that we learned first. Then later last year, we learned how to express this in more of a functional notation style. And so I'll write that down for our next example, and you'll groan and be like, oh yeah, this isn't hard, it's just different. Okay, we're graphing the set of real numbers where x is an element of the reals such that the absolute value of x minus 5 is less than 2. Okay, what we take from this is that we're graphing over the reals, not the integers, and this is our function, which we're totally used to doing, right? I'm just gonna write it over again. Okay, so our steps are number 1, isolate the absolute value on one side of the inequality. Done. The fact that that minus 5 is in there, there's nothing more we can do about that. This is isolated. Now we're ready to split it into 2 chunks that don't have absolute values. First, we just flick those off and we get x minus 5 is less than 2. And then we do it again where we copy this part, we flip the sign, and we make that a negative. Okay? Now this one, because it was a slightly more complex expression inside the absolute value, now we have a little bit of algebra to do here, but it's not hard, right? X is less than 7, and x is greater than 3. So now we want to graph that. So here's 7, here's 3. Remember that I don't need you to put all the details of the number line in there. Just put in the numbers that you need. What's more important to me is make sure you get this right? They're not inclusive of equals, so we have open circles, and we want what makes both of them true, which is the in-between. So that's my final answer. Let's do another one. These are fun, right? 22.3. Again, with the functional notation, I'll write it all down, although you don't need to do this necessarily. X is an element. Remember, that's a symbol for the reals, that R with the double thingy, such that the absolute value of x plus 2 is greater than or equal to 3. Okay? And again, that's our function. That's the part that we're used to seeing. So all this other stuff is just like, it's like sesame seeds on the outside of the hamburger. The meat is still the same. We just have a little bit of sesame seeds. It's just making it fancy. Okay, absolute value of x plus 2 is greater than or equal to 3. So here we go. Flick them off. X plus 2 is greater than or equal to 3. And then the other version, the absolute value part stays the same. We flip the inequality and give a negative to the other side. All right, I'll subtract 2 from both sides. X is greater than or equal to 1. X is less than or equal to minus 5. Now, as we look at this one, we realize this is not going to have overlap. This one's got, let's see, negative 5 is down here, and this will be 1. So it's less, x is less than or equal to minus 5, and it's greater than or equal to minus 1. So this one goes in the opposite directions. It doesn't meet in the middle, it goes to the outside. Yes, this is correct. All right. Okay. One more in this section. We have a second section in this lesson. But don't worry, it won't cause any drama. Example 22.4. None of it ever causes drama, right? Okay, sketch the graph of the function y equals the absolute value of x. Now, this is when we get some, they're not really alarm bells, but some red flags are going off, because this means now that we have two variables. And that means we have to switch to this kind of a graphing spectrum. If we only have one variable, like we did before in all of our other problems, variable, then we can graph on the number line. But when we have two variables, we have to go to this. So that's our big heads up that we're changing to this. Now, absolute value, you might remember the picture for this. We did it last year in the art lesson, which I don't think we've reviewed this year, but we can just do a quickie chart. Whenever you feel like you're in over your head in graphing, just draw a chart. You'll have an X and a Y, and then you'll have the function in the middle. That gives you some workspace to calculate. But this one's pretty easy. Let's start with 0. Absolute value of 0 is 0. Let's do a -1. Absolute value of -1. I don't know why I put parentheses on that. That's nonsense. It's +1. And then let's just do a positive number. 2, absolute value of 2 is +2. I draw my chart. Put a few of these on just so I don't have to draw while I'm graphing. 0, 0, -1, 1, +2, 2. And this reminds us, oh yeah, remember the basic absolute value is the flying goose formation thing, right? This is the shape of that function. Notice that it passes the vertical line test, right? Any line we could draw up and down would only hit one point on our flying geese. But if we draw this way, it does not pass the horizontal test to say that it is a one-on-one function. And I still need to do the research on what the difference is. Okay, so this is the answer to 22.4. John asked us to sketch the graph of the function y equals absolute value of x. And this is an absolute value function. And knowing that basic shape makes it a lot easier to graph these, because going in, you know what you're looking for, right? You know what this is going to be. Okay, that is all that I have to say about absolute values, but we want now to talk about a different kind of function. These are called reciprocal functions. And you know what a reciprocal is, and that's going to apply. If our function is y equals x, then the reciprocal function is y equals 1 over x. All right? And I don't want to give you a bunch of theory for this, because I want you just to focus on the practical matters of how to do these problems. So I'm going to skip a lot of the background that John gives us to try to explain it all. I think you trust John and me to just know it's true. If this is the function of y equals x, then the function of this, it goes out to 1, 1, and it curves. And these are those things called asymptotes that come close to this axis but never actually touch it. They go out to infinity. I'm not drawing them perfectly, obviously. I'm not a robot. But this is what the reciprocal function of a line will always look like. And like I said, I don't want to drown you in theoretical explanations as to why, but I want you to connect those in your brain. That this is y equals x, and this is y equals 1 over x. And when we have a linear shape, its reciprocal will always follow this pattern. And even if you forget that, again, whenever we need to graph something, if we can't remember the tricks of how to do it, just do a chart. So that's what we're going to do for the next and final example in this lesson. 22.5. Sketch the graph of the function y equals 1 over x squared. Okay, so this is not what we were just talking about. That was y equals 1 over x. So we really don't have a good picture of how to do that. So we're just gonna draw a chart and we're just gonna figure it out, right? So this will be x, and this will be 1 over x squared, and this will be y. Now, I would like to not make weird numbers over here. I want to have this come out nicely, right? So let's figure out how to do that. Let's start by using 1. This would be 1 over 1 squared. That's 1 over 1, and that would be 1. What if we put negative 1 in here? That would be 1 over negative 1 quantity squared, which again is 1 over 1, also 1. All right, this is looking highly graphable. Let's try 0. 1 over 0 squared, uh-oh, I just blew up the kingdom. This is undefined. That means our graph cannot touch at 0. That's a trouble spot. All right. Good to know. What about, I'm looking at my notes and finding out that this will get us a good answer, 0.5. That would be 1 divided by 0.5 squared. That is equal to 1 over 0.25. And 1 divided by 0.25 is 4. Good to know, right? And we'll do one more. Let's do 2. And that would be 1 over 2 squared, which is equal to 1 over 4. And let's just do 0.25. That we'll get close with that. I don't want to get too much crazier with my numbers. All right, let's graph down here where we have lots of room. I notice that all of my y values are positive, which makes sense because I've got a square on the bottom, right? So that would tell me that everything's going to go positive. All right, let's put some lines in. The first point is 1, 1. Got it. The second point is minus 1, 1. Got it. 0 undefined. Okay, so we're not allowed to touch this. Okay? No bueno. 0.5 goes up to 4. 1, 2, 3, 4. And I can also see, you know what, if I made this minus 0.5, it would also be positive 4. So I'm going to put another one over here, right? I'll just test it to prove it to you. If I choose minus 0.5, that's 1 over quantity minus 5 squared, which is also 1 over 0.25, which is positive 4. So I can put in the mirror of that one too. Same for this one. 2 goes with 0.25. And I also can see that if I did negative 2, that would be 1 over negative 4, right? It's 1 over negative 2 squared. And so that would be 0.25 positive also. This square is making everything positive. So 2.25. So what we get is a shape that some mathematicians very cleverly call a volcano shape. It will never touch the x-axis and it will never touch the y-axis, which is good because this is undefined, right? You're not allowed to touch it. These again are called asymptotes. They mean that they're curving lines that will never ever touch the vertical or horizontal line that they're approaching, all right? They'll come infinitely close, but they'll never actually touch. They're very hard to draw perfectly, so we just do the best we can. All right, that is this is the graph of this equation, and what's fun to see is I'm just gonna graph, this isn't part of the problem, but just for fun, let's graph y equals x squared, which is the partner to that, right? The non-reciprocal. That looks like this. It touches there, there, and there. And it curves out in a parabola like so. So look at the cool pattern that the parent function and the reciprocal function make together. It's kind of interesting how these go together. We're not going to take them too far. This is another topic, though, that shows up on placement tests and such. And if you can remember the way that these reciprocal functions look together, then that's a big help. But here's the thing. You can always just crank out a graph and use that to figure out what the graph looks like. The chart method is annoying, but it will always work. So put that ace up your sleeve when you're going forward. All right, that's all I have to say about this. We're going to talk about reciprocal trig functions at some point. We'll talk about other kinds of reciprocal functions even after that. I'm just thinking. I'm looking into your future and predicting what will come. So we will talk about reciprocal functions. Honestly, I think it makes a little bit more sense as we go forward. So if you feel like, I don't really know what this is, it's just saying that we can take any function that we know and flip it upside down and graph that too, and that the two, if you graph the parent and then the reciprocal, they make a cool picture together. That's all I want you to know. And you can use the chart method. Okay, I'm done. Goodbye.